what is hypothesis testing when you do it with means? Well, chapter 13, the first one, is going to look at it for a single mean, so that's what we're going to do today. And then you're going to look at it in terms of the difference between two means, but that's another day. So let's suppose we have a population, just one population. It could be Americans. And let's say it's their average age. We use the Greek letter that looks like that. You pronounce it mu, and that is the population mean. Now we have another fella called X bar. So you say it out loud. And he is the sample mean. And to remind you what a mean is, that's when you add them all up. Right, and you divide by how many there are. In layman terms, right? So let's suppose then that I would like to do a hypothesis test based on the population mean of America. And there's going to be a null hypothesis and an alternate. The alternate hypothesis is the thing you wish to prove. So let's say in my story that I want to prove that the average, right, the mean age of an American is more than 30 years old. You can do that. Mean age of an American is more than 30 years old. So we would write that down. Oops, don't know where that extra zero came from. Like that. The mean of the population is greater than 30. Right? This is called a one-tailed test. It's the name we give it. I would call it, in a lot of textbooks do, call it a right-tailed test, but a one-tailed test is what they're going to call it. And the null hypothesis is the same number as that guy. Now, do you notice that when we did proportions, it was P equals 0.12 and P was greater than 0.12. So based on what I saw in the test, a lot of you were not realizing that P is a proportion, right? A decimal has to be less than 1. So for instance, if you got a question and it was 17 out of 50 people said something, you went and put P equals 17 down. That's not the answer. P is not a number, a whole number, it's a proportion. On the other hand, these are numbers. These are going to be 17 and 40, but these will be the average weight of something is 17 or the average IQ is 40. So mu is a population mean, X bar is a sample mean. Mu equals 30 is the null hypothesis. That basically means nothing's changed, it's still 30. This is that it's greater than 30. Fair enough. We will have, just like in the other case, significance level. Let's say its significance level alpha is 0.05. Now you notice that's a decimal, always has been, always will be. Right? These will be nice numbers, typically not decimals. So how do I prove it? Well, what do? You go and get a sample. And I get a sample of 200 Americans. And I find that their average age is 33.5 years old. Right? And we would look at that and we'd say, well, yeah, that might be true then. the sample I got, they were older than 33 years old. And it might be that that's just randomness as well. So we have the usual kind of process, and there's going to be a lot of similarities between what we did last week and what we're going to do this week, right? Now, the types of things that we're going to do next is we're going to collect or calculate all the numbers that we need, right, to kind of move on to our final stage. One of the biggest differences about these is that although I'm going to be showing you one which is mostly done by hand, which it is, and the bit at the end is going to be done again using Solve. And then you'll find out that Solve gets used a lot more in these kinds of questions. In other words, a lot of the calculations I'm going to do will also be done by Solve, you'll find out. Whereas we used to do most of it by hand and just get the p-value. That's how we did last week. Here it's going to be, for many of the questions, different. So I got this guy. What do I need? I need to find the standard error of my sample. And the formula for calculating that one is going to be S over, darn it, still got my brain on. There we go. S over the square root of n. Can you remember that guy? It's a while back since we've seen that fella. You remember him? Right, same guy. Oh, so when I collected this data, I also collected the standard deviation, and it was 3.2, let's say. So the standard error is 3.2 divided by the square root of 200. On my calculator, that's 3.2 divided by the square root of 200. And that gets me roughly 0.226. That's kind of similar, isn't it, to proportions? You find the standard error, different formula, but still the same object. And then you get your guy that I call the Z-score. In fact, I'm not going to call it Z-score, I'm going to call it the T-score. It's a test statistic. Now, how's that going to be different? Right. When you do proportions, the distribution is typically going to be normal, and so you use a Z-score. When you do samples, especially small samples, this isn't that small, but when it is small samples, you're going to get a guy called the T-score. He is going to be made up of the mean of your sample. Take away a guy called mu naught, divided by the standard error of x bar. So this is the formula for the T-score. Now, if you're wondering who mu naught is, mu naught is just like P naught. Remember the null value, the null proportion? That's its names. This is the null value, the null value is 30. So I had a 33.5, take away a 30, divided by 0.226. Let's see what that looks like. 33.5, take away 30, divided by 0.226. And the answer I got is 15.5. So we have got a T-score. And then we get a guy called the p-value. And the p-value is the probability that you get a T-score greater than, less than, or not the same as. It's just like the usual. Right, you see how this guy is greater than 30? We want that. And this is when we would use salt. And let me show you whereabouts we get the calculation using salt. I think I've got it here. You should be looking at salt, are you? So in this story here, we need to click over to T distribution. And the first thing they're going to hit you with is degrees of freedom. It's been a while since we did this. Can you remember what the simple calculation for a degrees of freedom is? So there was
sample size minus 1.
Right. And since there was 200 in our sample, we'll make that 199. And we are wanting to be a greater than, right? So it's a right tail. And we want it to be greater than 15.5. Don't be surprised by the weird number. This number is so tiny that it's less than 0.00001, so we just call it 0. Now, can we just pretend that that number wasn't what I just said? Let's suppose that number was 2.8, right? Put a decimal point in. Imagine it was 2.8. Can you see your p-value would be that number, right? If it was 1.7, your p-value, click out there, would be that number. Do you see how we can calculate it then? So to get the p-value, you hit T distribution, you put the number in your sample minus 1, and then you put what you got in your t-score there, and the number underneath it is the p-value. In the case we just did, it was really 0, so that's what I'm using. Are we okay with how that process went? You see, it's very similar to last week, right? They may have different names, and you calculate things maybe a little bit differently, like the standard error, but it has a lot of the same kind of features. Now, once you've got to the p-value stage, just here, the next one, just like it should be, is the test. We ask, is our p-value less than the significance level alpha? In this case, our p-value was 0, and is it less than 0.05? And it is. And when the answer is yes, you can then state, well, you proved what you wanted. You've proved this, right? So you can say the null hypothesis, HA, is true. You can also say, and it's the equivalent to that sentence, you could also say, try to get this the right way, there we go. You could also say enough evidence to reject the null hypothesis. That's the same as saying that. You could say that we have proved statistically that the average age of Americans is greater than 30. That would be how I would say it, you know, if I was trying to describe to someone who didn't know statistics. Yeah, the average age of Americans is over 30. And we have proved it using this process. So the only place where salt right now kicked in, right? You see us here. So far, so good. Now, in quite a few questions in chapter 13, which we will eventually get to, you just focus on one piece of that puzzle, maybe just finding the standard error, maybe just writing the null and the alternate, right? And it's the later questions where you do the whole thing, right? But we're kind of, I'm jumping right into just doing the whole thing because I think that's helpful. So Hold on for a second while I wonder what the heck that question is doing there. Okay. Let's do some practice then. Just writing down these two. So that's all I'm going to be doing for the next few questions, is writing down how you would figure out what the null and alternate is based on a story. So if someone went and said, is there enough evidence to prove that the they can say the word average, I'm going to say mean, that the mean IQ for football players is less than 95. So imagine there was a story where they wanted you to see if you could prove this. Is the mean IQ of football players less than 95? Right, you'd set up a null and an alternate. The bit that really matters is that the mean IQ is less than 95. So that is mu less than 95. Are you comfortable how you would figure that out from the sentence I just read? Now, you tend to actually write this one down first, because once you've written this one down, what do you write as the null then?
Equals 95.
Equals 95. Isn't that very similar to P is less than 0.9, P equals 0.9, right? So this would be an example of an alternate hypothesis where you're trying to prove that the mean of something is less than, in this case, 95. My second one. Is there enough evidence to prove that I don't know, the mean height of French male adults is greater than, since they're French, it will be in meters, 1.8 meters. Okay, so what would the null, what would the alternate look like in this story? Anybody want to tell me what the alternate would look like in this story?
Mu is greater than 1.8 meters.
And what would the top one be then?
Mu is equal to 1.8 meters.
So can you see it's okay to have decimals, right? Right. That would not be a proportion story. You would never get a P, right? A proportion bigger than 1.8 or less than 1.8. You'd never get a proportion less than 95 or greater than 95. This would be our second situation. There's only three. Can you prove something's less than a number? Can you prove that the mean is bigger than a number? You know what the third one's going to be. Can you prove it's not equal to it? Right? Just like it was last week. Hopefully, while we're doing this one, it'll help you understand maybe where you were going wrong with last week's stuff, right? Because it's got a lot of structure, at least in the beginning, that's the same. So I'm not writing it there, enough evidence to prove that. So that is basically this. And this time that packet of flour is not 16 ounces. And I should say that the mean weight of a packet of flour is not 16 ounces. So you're buying flour out of some warehouse and you're getting a feeling that you're not getting 16 ounces. You're not sure what, but it just doesn't feel right, right? It might be that you're only getting, 15 ounces. It could be you're getting 17, but whatever it is, it ain't 16, right? It's not the same as. So in this case, the null hypothesis and the alternate would be mu isn't 16, right? It's not 16 ounces. And this would be mu equals 16. And this guy is called a two-tailed test. This guy, according to the textbook, is a one-tailed test. And this is a different kind of one-tailed test. Do you feel comfortable about reading a story and writing down what the null and alternate would be in each of these situations? Right, so we're just taking that one, the first step into the test. Feel good with that? So let me see if I can find one. Okay, here's question 6 from the homework. A botanist for a large rose farm is told that the company currently average $452,000 in sales annually. The company hires her to work as an outside consultant in order to increase their annual sales revenue. The null hypothesis is H naught is mu equals 452. Right. I'm going to jump to B first. Which, oh darn it, I just noticed. I wish I would stop doing that. Pretend you never saw that answer. It still doesn't want it to go away. I'm really annoyed at this machine for doing that. Right. You never saw it, right? So they hired this consultant and she's going to improve their sales. So which one of them do you think is the alternate hypothesis, the thing that you want to prove to be true? Equal to that, not equal to that, less than that, greater than that. There's your choices.
Greater than 452.
Right, so hopefully you can't remember, that's the one they were pointing at, right? Now, is this a one or two-tailed, or you cannot tell?
One.
Yeah, pretty easy to tell. Great. Why is it giving solutions? It really doesn't want to. There we go. It's helpful sometimes if I've got answers, but it's more of an annoyance. Okay. Question 7. A chemist believes that a cornfield must be treated with a fertilizer on average 5 times over the year if he wants to get a good crop. Okay. However, she's curious if she could do just as well by using fewer. Right, so instead of doing it 5 times on average, maybe she could do it just 4 times. The null hypothesis is 5. What do you think her alternate is going to be? They've even set up most of the thing. Less than, greater than, or different from 5, based on the story that she's curious if she could use fewer treatments.
Be less than 5.
Yeah, she's thinking, I wonder if I could do less. Now you can imagine what she would do then if she had time. Couldn't she take one of her fields and just do the normal 5 deal? And then a different field, she just does 4 on it. And then she, you know, once harvest comes, she figures out, hey, there wasn't really any difference. That's great. I can save money, right? I don't need to do it 5 times a year. I'll do it 4. Could be that that isn't what's the case, in which case she'll say, okay, then I'm not doing that again. Would you agree that's a one-tailed test? Okay, here's another one of these setup stories. A botanist believes that the pumpkin patches must be treated with a fungicide 6 times in a year to get a good crop. Again, she's curious, so it's the same story, but they've just given you a little bit less of a start. Less than, equal to. Have you noticed it's always equal to for the null? You don't have a choice. And isn't it always equal to the same number that's used on the alternate? So if you know you're trying to prove something's less than 6. If you're trying to prove something's bigger than 6. If you want to prove that it's different, not equal to 6. Okay. So in this question here, we're defining the parameter of interest, which just means what are we interested in, right? Is it how much times you fertilize the field, or is it the average age of someone, whatever it is? That's the parameter of interest. So the bit I'm interested in here is this, right? So I'll skip that answer, you can do it yourself. So how many cars have a recommended tire pressure of 33 PSI, pounds per square inch? So that's what they're interested in. At a roadside vehicle safety checkpoint, officials plan to randomly select 50 cars for which it is recommended that the tire pressures measure the front and left tire. They want to know whether the drive average are too little. So that is the guy, and they want to see if it's too little, right, too much. Right? So they should be 33, and they just do a roadside check. Oh, that one's 35, that's a bit too much. That's 28, that's almost flat, right? They go through the cars. What? We are interested in the null and the alternate. That guy's 33. So you want to do mu equals. So I'm going to hit the Greek letter, and there's nu. And I know it's going to equal 33. Now, is this story, we wonder if it's different, we wonder if it's bigger, or we wonder if it's less? Which one is this story about?
Less.
Do you see it there? On average, have too little pressure. So that's going to be mu, Greek letter again. Well, actually, you can kind of copy that letter if you want. Hopefully, Control C. And less than 33. Okay, next story. This is a, can I click on that? Good. The box of Yvette's favourite cereal states that it has 13 ounces in it. But she's suspicious of this claim because the package never seems full to her. She thinks she's getting less than what they told her. So she plans to measure the weight of the contents of the next 30 boxes and she buys to find out whether she's been shortchanged. So we need a null and we need an alternate hypothesis for her little story. Now, the null hypothesis is going to be that mu is equal to 13 ounces, right? That means she's getting what she should be getting. Now, what does she suspect? Well, she thinks and she wants evidence to prove that she's being shortchanged. What does that look like as an alternate when you're looking for evidence you're being shortchanged?
Mu is less than 13.
When you do a hypothesis test, if you don't get that bit right, do you know what happens after that is going to be kind of wrong, 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 and wrong, right? It's a bit like if you start with adding two numbers and you add them up wrongly, won't every calculation after that not work, right? So it's kind of important that you know how to set these things up. Let's just leave that guy. And I'll return to my notes. Do we need to do any more of these? Are you comfortable about setting these guys up? Right, so let's move on to the next phase. If you remember what the next phase was, let's find t-scores. Right. Let's calculate t-scores. Now, in order to get t-scores, I need to know a sample mean. I need to know this guy, but this guy is that number there, right? And I need to know the standard error, right? So that's all the pieces that I need in order to get the t-score. So just pick one of my stories. That's a good way of doing it. Let's suppose I was doing the one about the IQ of football players, right? And I just want to find the t-score. So I collect 250 football players and I give them an IQ test and I find out that their IQ was 93. And I get the standard deviation of my 250 was 1.7. Right? So those numbers I typically need to be told, right? I won't necessarily calculate them, right? So you'll get them for free. So all I need to do now is find the standard error, and then I can get the t-score. So these numbers you will be given. Right? This you will calculate. And the standard error is the standard deviation divided by the square root of the sample. So in this case, it would be 1.7 divided by, the square root of 250. In this case, 1.7 divided by the square root of 250 ends up being 0.11 to 2 decimal places. And now the t-score. It's the mean, take away that guy over the standard error. And the mean was 93. And that guy, I'm here, he's mu naught. He's the null value. So it's going to be that guy, take away 95, divided by 0.11. So I'll go 93, take away 95, divided by 0.11, and I get the answer negative 18.18. Are we comfortable about that one? Does it seem okay? Use this formula here to get the standard error. Use this formula here to get a t-score. You need to know that before you can do that. Okay, there's one done. Do this story then. We want to prove that the mean height of Frenchmen is more than 1.8 meters. So I get the government to pay me a large fee to do this research for them. And I go over to Paris for 6 weeks and I ask, oh, well, no, don't ask. I get 100 random Frenchmen, and I get their heights. Their heights was 1.91 meters, and the standard deviation was 0.3 meters. And that I was given, right? Now I'm going to get the standard error. Which is that guy. And then I can get the t-score, because that's what we're being asked to find. The t-score then is the mean, take away mu naught over the standard error. And the mean is 1.91. And this guy is 1.8. And it's going to be divided by 0.03. And the answer I got, let's see, 1.91, take away 1.8 is that guy, and it's going to be divided by 0.03. It looks like I got about 3.67. Did you notice that calculating the t-score is the same, whether I'm trying to prove something's bigger than a number or less than a number? You notice that the standard error doesn't care what that is, the t-score doesn't care what that is. So that bit's not going to cause you too much trouble, even if you get this wrong, right? Because that and that are independent of that decision. Are we good? So I'm going to do, I won't show you, I'll just use the question numbers. And this is an example of question 10 from the homework. And you're told basically all the stuff that you need. Actually, you're kind of told stuff you don't need as well. I forgot to put H naught there. There we go. You told that guy, you told that guy, you told that guy, and you told that guy, right? And you're being asked to find the t-score. So I'll start with the standard error. 70 divided by the square root of 121. And I get about 6.36. T-score is going to be that calculation. So it's going to be 65. Oh, sorry, 40. 65 take away 45. I'm going to do it the wrong way around there. And the standard error is 6.36. So 65 take away 45 divided by 6.36, and the answer I get is 3.144. Do you want to see some more of calculating t-scores, or do you feel comfortable about them now? We're good. Right. So next phase is to get the p-value. You see how the question we did at the start was the whole process. All I've done now is I've said, okay, let's do some practice at getting null and alternate. Check. Let's do some practice now at finding t-scores, right? Check. So now let's do some practice at finding p-values. Suppose I have a null hypothesis that the mean is 20, and the alternate hypothesis was that we'd like to see if it's bigger than 20, right? And we have got X bar is 21.5, the N was 30, the standard deviation was 7, right? We got all those guys. So this we're told, right? And we are going to find p-value. So we have to kind of go through some of the stages that we've done so we can do one more extra stage at the end. And when you're asked to find the p-value, you are going to use solve, right? There's no way around it. You need to use solve. So I'll begin with calculating the standard error. In this case, the standard error is going to be S over the square root of N. It's going to be 7 over the square root of 30. And the answer we got here is 1.28. Now, after that guy, you need to get the test statistic, which is what the t-score is called in this case. And it's going to be X bar, take away mu naught over standard error. X bar is 21.5. Mu naught is 20 divided by 1.28. So see what that is. 21.5 take away 20 divided by 1.28, and the answer I get is 1.172. And now I get the p-value. P-value is the probability that I get a t-score greater than, less than, or not the same as this guy. Well, you get that from here. You want to prove it's bigger than, so it's greater than this number. And what I'm going to do now is go to the calculator, or go to solve, I should say, and find that answer. Maybe shrink this down a little bit. Okay. Am I in the right distribution? Hopefully you can see it says over here normal distribution. Is that the right distribution for this question?
No.
What should it be called?
T distribution.
Right. Now, I need to know degrees of freedom. Well, in my sample, there was 30 people, so isn't that 29? In my story, aren't I looking for bigger than? And if it's bigger than, isn't it a right tail, right? That's why I like the name right tail test, right? Bigger than. And what number do I want to see if it's bigger than? I want to see if it's bigger than 1.172. And this guy here, that's where the p-value lives. So the p-value in this question happens to be 0.12, let's say 5. And tomorrow we'll continue with this.